when the James Webb Space Telescope finally turned its golden eye toward Pluto. It wasn't just to take another pretty picture. It was there to hunt for the solution to a decade-long mystery, one that began with a single, shocking number. Pluto, it turns out, is far, far colder than it has any right to be. And the reason why, which we have finally confirmed, flips a fundamental rule of how planets work. It's a discovery that doesn't just rewrite the textbook on Pluto. It may force us to rewrite the textbooks on planets everywhere, and even on the origin of life on Earth. If discovery is your thing, subscribe to Stellify Science and turn on notifications so you never miss what the universe reveals next. For almost all of human history, Pluto wasn't a place. It was a ghost. Discovered in 1930 by a persistent young astronomer named Clyde Tombaugh, who painstakingly compared photographic plates, Pluto remained one of the great agonizing mysteries of our solar system for the rest of the 20th century. For your parents, your grandparents, and their grandparents, it was the final unknown frontier. Through even our most powerful telescopes, it was just a faint, flickering dot of light, a pinprick against the infinite black. Its existence was more a mathematical certainty than a physical reality. It orbits in a realm of perpetual twilight, more than 5 billion kilometers from the Sun. The distance is so vast that our star, the furnace of our world, would appear in Pluto's sky as little more than an extraordinarily bright star, casting a weak, silvery light. Astronomers knew it was small, about 2/3 the size of our own moon, and they knew it was icy, a frozen relic from the dawn of the solar system. They had theories, of course. They suspected it might have a thin, fragile, and perhaps temporary atmosphere. This atmosphere, they guessed, was a ghostly shroud that could possibly freeze and literally fall to the ground as snow as Pluto moved farther from the Sun on its long, looping 248-year orbit. An entire sky, frozen solid and collapsing onto the surface. But beyond these vague ideas, these educated guesses, there was no data. There was only speculation. That all changed on July 14, 2015. After a grueling 9-year, 3 billion-mile journey across the entire solar system, NASA's New Horizons spacecraft, traveling faster than a speeding bullet, screamed past Pluto. This wasn't just another mission. This was a race against time. Scientists had feared that if the spacecraft wasn't launched by 2006, it wouldn't reach Pluto before that very atmosphere froze and collapsed. We could lose our only chance to study Pluto's atmosphere up close, possibly for centuries. The mission had to make it. It was our one shot, and what it revealed stunned the entire world. Pluto wasn't a cold, dead rock. It wasn't a lifeless and dull sphere of ice. It was alive. The images New Horizons sent back were not of a simple world, but of a story. We saw towering mountains, as high as the Rockies, but made not of rock, but of solid water ice, frozen harder than granite at those temperatures. We saw vast, smooth, impossibly young plains, glaciers made of frozen nitrogen and methane that were actively flowing across the surface, like a slow-motion river of solid gas, erasing impact craters and constantly renewing the landscape. This distant dwarf planet, this ghost, was shockingly, wonderfully dynamic. But perhaps the most beautiful and utterly unexpected discovery was floating above it all. A fragile, complex, and deeply mysterious atmosphere. It wasn't thick, but it was there. It was made mostly of nitrogen, just like Earth's, but with traces of methane and carbon monoxide. And it glowed. As New Horizons looked back at Pluto, it captured one of the most haunting and iconic images in modern space exploration. The atmosphere, backlit by the distant sun, glowed with a faint, ethereal, and distinctly bluish haze. This haze wasn't just a single layer. It was stacked in the sky, in dozens of separate, distinct layers, like rings in a tree, stretching more than 300 kilometers above the surface. It was beautiful. It was magnificent. But as scientists analyzed the data, they realized that as beautiful as it looked, something didn't add up. This is where the fairy tale ends and the detective story begins. Something was terribly, fundamentally wrong. That stunning hazy atmosphere was far, far colder than anyone had predicted. Before New Horizons ever arrived, scientists had run the numbers. They built sophisticated computer models to estimate what Pluto's upper atmosphere should be like. These models are the backbone of planetary science. They are how we understand and predict the behavior of worlds we can't visit. They fed in all the variables they knew: Pluto's immense distance from the Sun, its atmospheric composition, mostly nitrogen with that bit of methane and carbon monoxide, and the faint but predictable amount of solar radiation it receives. The models all agreed. The temperature of Pluto's upper atmosphere should be somewhere around 100 Kelvin. For context, 0 Kelvin is absolute zero, the point where all atomic motion ceases. 100 Kelvin is about 173 degrees Celsius, or 280 degrees Fahrenheit. That is, of course, incredibly, unimaginably cold. But it was the expected cold. It was the number that made sense. It was the equilibrium temperature, the balance point where the tiny amount of energy Pluto gets from the Sun equals the energy it radiates back out into space. But when New Horizons actually flew through that atmosphere, dipped its instruments in, and took direct measurements, the results were shocking. Pluto's atmosphere wasn't 100 Kelvin. It was 70 Kelvin. That 30-degree difference might not sound like much to us, but in planetary physics, at these temperatures, it is a chasm. For planetary scientists, this was a huge gaping hole in their understanding. It meant that their models, the very tools they use to understand planets across the universe, were fundamentally, spectacularly wrong. This isn't like finding your home thermostat is off by a degree. This is like coming home to find your entire house is a solid block of ice, even though you know the furnace is running exactly as it should be. Some unknown process, was cooling Pluto's atmosphere, and it was cooling it with terrifying efficiency. Bleeding heat out into the blackness of deep space far faster than any known gas could. But what? What could possibly be acting as a giant, planetary-scale air conditioner, so powerful that it defied all known models? The answer, it turned out, was hiding in plain sight. It was the haze itself. To understand what's happening, we first have to ask a more basic question. How does a world 5 billion kilometers from the Sun, a world with almost no heat and almost no air, even have a haze? How do you get smog in a realm of perpetual twilight? The haze on Earth, for example, mostly comes from moisture, fog, dust, or pollution near the surface. Pluto's haze is something else entirely. It's alien. It isn't born from the ground. It's born from complex chemistry happening high in the sky. And it all begins with the one thing Pluto has very little of: sunlight. Even though Pluto is incredibly far away, so far that the sunlight it receives is 1,000 times weaker than what we feel on Earth, it's not zero. Faint but relentless ultraviolet rays, the same high-energy light that gives us a sunburn, stream across the solar system. This UV light carries just enough energy to act like a tiny, precise cosmic hammer. This is the first step: shatter. When one of these UV light bullets hits a methane molecule, which is just one carbon atom and 4 hydrogen atoms. It shatters it. The molecule breaks apart, perhaps into a methyl radical, CH3, and a hydrogen atom. This is where the magic starts. This is step 2, combine. These broken reactive fragments don't just float away. They are chemically unstable, like tiny Lego bricks with exposed studs. They are desperate to become stable again. They start reacting with each other, sticking together, and forming new, more complex molecules. They build things like ethane, ethylene, and acetylene. These are all types of hydrocarbons, molecules that are heavier, more stable, and more tar-like than the simple methane gas they started as. Then comes the final crucial step, grow. This process doesn't stop. It's a chemical snowball. These new molecules keep combining, linking up into longer and longer, more complex chains and compounds. Eventually, they grow so large and complex that they are no longer gases at all. They condense and become solid, tiny, sticky, tar-like particles. Scientists have a name for this complex reddish-brown organic gunk: tholins. These tholins are tiny, solid bits of organic matter. They are, in a very real sense, sun soot, born in the sunlight, high in the sky. As these solid particles slowly drift downward through Pluto's thin atmosphere due to gravity, they begin to clump together. They gather and form those distinct, visible layers of haze that New Horizons so beautifully captured. This haze, by the way, is what gives Pluto its blue sky. Just like on Earth, this is a process called Rayleigh scattering. The tiny tholin particles are just the right size to scatter sunlight in a way that favors bluer wavelengths. So, if you were to stand on the icy surface of Pluto and look up, you would see a soft, pale blue sky, all thanks to this complex organic smog. This process is more like what we see on Saturn's largest moon, Titan, which is also shrouded in a thick orange, organic haze. But on Pluto, this haze turned out to be far more than just a pretty feature. It was the central clue to that 30-degree mystery. For years, researchers were stumped. They compared data. They refined their models, but nothing could account for the missing heat. Then, in 2017, a planetary scientist named Shi Zhang from UC Santa Cruz proposed a bold, unconventional, and, at the time, almost crazy idea. The question was, what if the haze wasn't just a passive feature? What if it wasn't just floating there, scattering blue light and looking pretty? What if the haze was actively controlling the planet's temperature? Here was Zhang's groundbreaking hypothesis. These tiny tholin haze particles are dark and tar-like. Like a black t-shirt on a sunny day, they are extremely good at absorbing sunlight. So, as the faint sunlight hits the haze layer, the countless tiny tholin particles soak up that energy and get warm. But then, and this is the absolute key to the entire mystery, they have to release that energy. They re-emit it, not as visible light, but as heat in the form of mid-infrared radiation, which is a color of light our eyes can't see. Think of it this way. Imagine billions upon billions of microscopic black radiators, all floating in the upper atmosphere. They catch the faint sunlight, heat up, and then beam that heat right back out into the cold vacuum of space, in all directions. On Pluto, where the atmosphere is incredibly thin but also packed with these haze particles, Zhang proposed that this process could be powerful enough to cool the entire atmosphere. The haze wasn't just in the atmosphere. It was the atmosphere's thermostat. It was acting as a giant global cooling system. This idea was truly radical. It flew in the face of decades of planetary science. Until then, scientists had always believed that an atmosphere's temperature was controlled by its gases. On Earth, for example, it's the broth, gases like carbon dioxide and water vapor, that holds the heat and drives the climate. The particles, dust, soot, haze, are just the croutons. They're in the soup. They might affect it a little, but they don't set its fundamental temperature. Zhang's idea was that on Pluto, the croutons were the entire cooling system. The notion that solid particles could dominate this entire process, that they could be more important than the gases, that seemed strange. It was a huge paradigm shift, and it was hard for many in the community to accept. But Zhang's idea made a very specific, testable prediction. If Pluto's haze was indeed cooling the atmosphere by radiating heat, then it should be glowing with a specific signal. It would be emitting a fingerprint of light in the mid-infrared part of the spectrum. If we could point a powerful enough telescope at Pluto, we should be able to see the haze itself glowing with heat. There was just one problem. It was completely and utterly impossible to test. At the time, in 2017, no telescope on Earth or in orbit had the precision to detect such a faint and specific signal. The observational challenges were immense. First, Pluto is tiny and incredibly far away. Its heat signal is unimaginably faint. Second, and this was the mission killer, Pluto has a large moon, Charon, that orbits very close to it. Through existing infrared telescopes, the two worlds were just a single, blurry blob. Their heat signatures were hopelessly blended. It was like trying to hear a person whisper while they are standing right next to someone who is shouting into a megaphone. You can't separate the two sounds. Any data we got was hopelessly contaminated. The shout of Charon's reflected heat completely drowned out the whisper of Pluto's atmospheric glow. Zhang's crazy idea, as elegant as it was, remained just that. A brilliant but untestable theory. It was stuck in theory prison, waiting for a key, but all of that was about to change. In 2021, a new chapter in human exploration began. The James Webb Space Telescope launched, unfolded its massive golden mirror, and cooled to its operating temperature, deep in space. Webb, with its enormous 6.5-meter mirror, was built to peer into the coldest, faintest, and most distant corners of the universe. It was the perfect tool. It was the key. It was the only machine ever built by humanity capable of finally testing Zhang's bold theory about Pluto. One instrument on board was especially important. MIRI, the mid-infrared instrument. MIRI wasn't just a camera, it's a heat seeker. It was specifically designed to detect light in the 4.9 to 27 micron range. This was exactly the part of the spectrum, the color of heat, where Pluto's haze particles would be glowing, if they were, in fact, cooling the atmosphere as Zhang had proposed. The untestable theory was suddenly, finally testable. Then, in May 2023, the moment of truth arrived. An international team of scientists, led by Tanguy Bertrand, pointed the James Webb Space Telescope directly at the Pluto-Charon system. And immediately, before they even analyzed the specific glow, Webb achieved a massive breakthrough. For the first time ever, scientists could clearly separate the two worlds in infrared light. What was once a single, fuzzy, blended blob of heat in every other telescope was now two distinct, sharp, perfect points of light. Webb's powerful vision, its incredible resolution, had finally resolved the system. Webb didn't just look at Pluto. It dissected it from its moon in infrared for the first time in history. This was the first victory. It allowed researchers to cleanly isolate the thermal glow of each object. They could finally listen for Pluto's whisper, without Karen shouting over it. This is how they did it. The team used MIRI to gather detailed data on the heat coming from the whole system. Then, they built a highly accurate computer model for Karen's heat signature. And then, they simply subtracted it. They took the total data from the blob and subtracted the unknown data from Karen. What they were left with was a clean, pristine picture of Pluto's own mid-infrared emission. And when scientists examined that leftover glow from Pluto, they spotted the smoking gun. The infrared glow coming from Pluto was stronger than what its icy surface alone could possibly produce. That meant something else. Something above the surface was radiating heat. If Pluto were just a dead, icy ball, it would be much fainter. The signal Webb got was brighter. It was an excess of infrared light. The atmosphere itself was glowing. This became even more obvious when the team looked at the data in microscopic detail. Let's walk through the evidence, because this is the moment the mystery was solved. This is the payoff. This figure from the research paper shows how much heat Pluto is emitting at 4 different colors of infrared light. The goal was simple. Figure out how much of this heat is coming from Pluto's icy surface and how much is coming from its hazy atmosphere. Now, look at the bottom row of the figure. This is the key. The black dots are the actual observations. This is reality. This is what Webb's MIRI instrument actually saw. This is the ground truth. This is the number we have to match. Now, look at the lines. These are the models, the theories. The purple line represents theory number 1, the ice ball model. This is the calculated heat from only Pluto's icy surface. And as you can see, it's a catastrophic failure. The purple line is way below the black dots. This model is wrong. The ice alone cannot explain the glow Webb saw. Now, look at the cyan line. This is the new idea. This is the model for the heat being emitted by the atmosphere alone, specifically from those Tholen haze particles. And finally, the gray line. The gray line at the top represents the grand total. It's the ice ball model added to the haze model. And here's the key point. The gray line matches the black data points remarkably well. It's not just close. It's not just good. It is a near-perfect match. The gray line lands on top of the black dots. It is the black dots. This is the moment. This is the EMC2 of this discovery. That perfect fit is the definitive proof. It confirms with hard evidence that the only way to explain reality, the black dots, is to include the heat being radiated by the haze, the cyan line. Pluto's haze isn't just floating in the background. It is glowing in the infrared. It is actively radiating heat into space. It is the primary cooling agent. It is the planet's thermostat. What was once just a speculative, crazy idea in 2017 is now backed by hard, irrefutable evidence from the most powerful telescope ever built. The mystery of the 30-degree gap is solved. The haze did it. So, why does this matter? Why is Pluto's haze such a big, game-changing deal? Well, on most planets we know, like Earth, Mars, or Venus, it's the atmospheric gases that do all the heavy lifting when it comes to climate. Gases absorb sunlight. They trap heat, and they radiate energy back into space. Tiny solid particles like dust or aerosols might contribute a little bit, but they've never been the main driver. Pluto changes that. For the first time, we see a world where the haze, the solid particles, the soot, not the gases, is in charge. The solid Tholen particles are not just drifting in the background. They are actively and dominantly cooling the entire atmosphere. Pluto has flipped a long-standing fundamental assumption in all of planetary science. For decades, we had two main kinds of climates: rock-based, like Mars, and gas-based, like Earth or Jupiter. Pluto has just given us a third category, the haze-driven climate. It's a new page in the textbook. It's a new class of world. This discovery forces us to reconsider everything we thought we knew about cold, distant worlds. Pluto might not be the only world where this happens. Other cold, distant bodies in our own solar system, like Saturn's moon Titan or Neptune's moon Triton, also have thick, nitrogen-rich atmospheres that are filled with haze. Until now, scientists assumed gases alone explain their temperatures. But this discovery forces us to ask, if haze is cooling Pluto, could it also be shaping the climates of these icy moons? Are all our models for Titan wrong? We have to go back and check. Second, the implications stretch far beyond our solar system, to the hunt for life elsewhere. We are discovering thousands of exoplanets. Many of them, especially those orbiting far from their stars or cloaked in their own hazy atmospheres, may not follow the rules we've been using. Our traditional, gas-based models for climate and habitability might be completely missing the mark. We might look at a distant hazy exoplanet, run our old gas-based models, and declare, it's too cold for life. But what if it's not? What if it has a haze-driven climate that's stabilizing it in a way we've never accounted for? This discovery adds a brand new, critical variable to our search for habitable worlds. And perhaps the most intriguing, most profound implication echoes right back to our own planet. This mechanism may be a window into Earth's own distant past. Scientists have long puzzled over the faint young sun paradox. Billions of years ago, our sun was significantly weaker and dimmer than it is today. By all accounts, the early Earth should have been a frozen snowball. Yet, we have geological evidence that Earth had liquid water and was quite warm. How? The leading theory involved a thick greenhouse blanket of gases like carbon dioxide and methane. But Pluto offers a new, stunning possibility. Around 2.4 billion years ago, before the Great Oxygenation Event, Earth's atmosphere was totally different. It had very little oxygen. It may have resembled Pluto's atmosphere, rich in nitrogen and hydrocarbons, with thick organic hazes formed by ultraviolet light. It's possible that these ancient hazes, just like Pluto's, help to regulate Earth's temperature. They could have absorbed harmful UV radiation while also managing the planet's heat, creating a stable, protected cradle for life to emerge and thrive. Pluto, then, isn't just a dwarf planet. It's a time machine, showing us a climate model that may have been the very one that nurtured life on our own world. And that wasn't the only discovery Webb made. Because Webb was able to so cleanly separate Pluto from its moon Charon, scientists were able to solve another long-standing mystery, the case of Charon's dark red cap. New Horizons first spotted this weird, reddish-brown stain at Charon's North Pole. It looked like something had spilled. JWST's data confirmed that Pluto is slowly leaking its atmosphere into space. Specifically, it's leaking methane gas. And some of that escaping methane is being caught by Charon's gravity and is falling onto the moon's poles, where it freezes. There, on Charon's cold poles, that imported methane ice gets exposed to sunlight and cosmic radiation. This triggers the exact same chemical reactions, cooking the methane and turning it into complex reddish-brown tholins. Charon's red cap is made of Pluto's leftovers. It is, literally, Pluto's atmosphere, stolen by its moon and painted onto its surface. What started as a simple mystery about Pluto's cold skies a 30-degree error in a model, has turned into a story with cosmic significance. We've found a new kind of climate. We've found a new way for a planet to function, one that reshapes how we understand moons, exoplanets, and perhaps even the origins of life itself. Pluto, once a blurry dot, a ghost, a dead world, has turned out to be one of the most important and dynamic teachers in our entire solar system. If this changed how you see Pluto, watch this next on the strangest molecule signatures beyond Neptune to keep the story going.